Can everybody hear me all right? Yes? Okay. All right. Well, I'm supremely conscious that I'm keeping everybody from lunch, so I'll see if I can't be reasonably terse here. Dante Loretta, the PI of the mission, couldn't make it. He sends his apologies, but hopefully I'll be a decent substitute. Okay, there'll be a test on this later. The OSIRIS-REX acronym is kind of complex. In fact, I can't be reliably counted on to repeat it quickly. So I'll just go through it here from the slide. Origin, spectral interpretation, research identification, security, regolith, explorer. Okay, that's quite a mouthful. I won't go through what each of these comes from on this slide because basically we'll get to these points in subsequent slides. OSIRIS-REX is a NASA-funded mission. It's a New Frontiers mission. It's going to be launched in 2016, so we're getting close. It will rendezvous with an asteroid, 101955 Bennu. It'll collect a sample in 2019. It'll also do a bunch of remote observations while it's there. I'll get into that in more detail. And then it returns a sample to Earth in 2023. So this is in some ways a mission for patient people, particularly those like me who are sample analysts. But the asteroid Bennu is a B-class asteroid. We think it's fairly primitive type asteroid in the sense it hasn't had lots of alteration of its surfaces and materials. And so we hope that this will allow us to learn from the samples things about the origins of the Earth, the solar system. We'll hope to find organics on this object, which may tell us something about the formation of life on Earth. We'll certainly learn a lot about the composition and structure of asteroids, particularly this one. Since we'll have a lot of ground truth, both in terms of close-in observations made while we're at the asteroid, as well as actually having the samples in our hands when they get back, we'll be able to compare these results to the kinds of observations you traditionally get from asteroids through telescopes and try to put some ground truth on what those observations mean. And this would then therefore allow us to take the information we get from Bennu and actually extrapolate it to a much larger population of asteroids. And then one of the things we're doing, which is kind of unique to this mission, is we're going to look at how sunlight impacts the course and speed of asteroids. This is a Yarkovsky effect. I'll talk about this a little bit more in detail. Since I can't assume most of you are familiar with it, I'll even give a little description of what this actually means. But first, since I'm a sample guy, I want to proselytize a bit about the advantages of sample return missions. I debated what to put in the background here. I could have put in a Stardust Comet Sample Return Mission picture, or a Hayabusa Asteroid Sample Return Mission picture, or a Genesis Solar Wind Sample Return picture. I had the joy of participating in all those missions in some way. But given yesterday's anniversary, I thought it may be more appropriate to do this, because this was also a sample return mission, one I actually did not have the joy of being involved in, although I have returned lunar and Martian meteorites from Antarctica. I should mention that July 20th is actually a special day for me for more than one reason. Yesterday was the 45th anniversary of the landing, but it was also my 29th wedding anniversary. And it took me 5 years to get the courage to tell my wife the reason I lobbied so hard for July 20th for our wedding was because it gave me a marginally better chance of remembering the date. She took it pretty well. And as a ploy goes, it's mostly worked. So anyways, what are the advantages of sample return missions? Actually, sample return missions are difficult because, at least in one very unique way, which is that they can't go to some place and then be done. They have to come back, and that's quite a bigger challenge because your spacecraft is older, you're running out of fuel, nothing's working quite right, and so on. But fortunately, it's worth it for a number of reasons. First of all, normally when you fly a spacecraft to an object, you have to fly instruments that are robust, you know will survive, and in addition it takes you a long time to get there and time to make them before that. And so most instruments that actually measuring things on spacecraft are not really state-of-the-art in terms of the analytic capabilities of things, but if you bring the sample back, then you can carry it into any laboratory you want on the planet, and sort of by definition you can take advantage of state-of-the-art analytical techniques. So you really get the ultimate in precision, sensitivity, resolution, and so on. In addition, of course, the return samples are a resource for current and future studies. You don't get the samples back, study them for a few days, and then throw them away. They go to a curatorial facility, and then they're available in perpetuity. So, for example, even though we're in the 45th anniversary of the return of samples, essentially, people are still learning about the moon because they're studying these samples. And so any time you return a sample, you have that advantage. Also, your analyses can be iterative and fully adaptive. If you're going to fly to a place and make a measurement there, you have to decide before you go what you're going to measure. And if you decide the most important thing is to measure A, and you go there with your A measuring machine and you measure A, it's always possible that the main thing you'll learn from measuring A is that maybe you should have measured B. Okay, now you need a new spacecraft and another mission. But if you do this with a sample return, you just don't sweat it. Take it out of the A measuring machine, go down the hall to the B measuring machine, and get on with things. So also you avoid limitations associated with cost, power, mass, and reliability. Some of the instruments we use to study Stardust samples from Cometville 2 were not just bigger than the spacecraft, they're bigger than the launch pad from which the spacecraft left. Okay, so no one's going to fly a synchrotron to someplace to take Zane's spectra of organics in that object. So, and then of course the analyses can be replicated, verified, done with multiple techniques. So this is sort of a fancy way of saying a lot of people can get in the game and argue about it. Okay, and so the net result is you can learn a lot of things this way. You won't learn any other way. Two astronomers on adjacent peaks may be able to figure out what each other's favorite colors are with telescopes. They might know what time they eat lunch. Neither one's going to know the other one's biochemistry is based on DNA until they go over there and jab a needle in them. Okay. Okay, so our target asteroid is Bennu. This on the left is a radar data, and on the right is a shape model based on that. You can see it's a fairly spherical object. Shows a hint of an equatorial belt, which may be associated with material moving towards the equator under the effects of the rotation. It happens to actually have its pole pretty near to perpendicular to the orbit, which is good for us on the mission because it means most of the surface will be in sunlight at some point or other. We don't have to worry about any dark poles that never get into the light. Here's some information about, whoops, wrong button, about the semi-major axis. Its mean diameter is just a little under a half a kilometer, so it's not a particularly huge object. Its rotation period is known pretty precisely here. It has very low albedo, which is what you would expect for a B-type asteroid, and this gives us some hope that we have organics and other primitive kinds of things on the surface. And based on the radar data and other observations, we are pretty sure the bulk density falls in this range right here. And then fortunately for us, a lot of observations support the presence of the existence of an abundant regolith, which is ideal for sampling, something where it's not concrete sidewalks and not loose talcum powder. And one thing to keep in mind is Bennu comes within 0.003 AU of the Earth, and I think it's the asteroid that has the highest single impact probability of any known asteroid with the Earth. So anything we can understand both about it as an object and also its orbit would be a highly interesting thing to know. Okay, so Bennu's small, but it's not that small. Okay, this is just to put it to scale to folks here in the Bay Area. I hope you all get to see wonderful images of Bennu, but not this one. I can't think of many advantages of seeing this image other than the fact that you don't have to worry about your homework. I believe the profile of the object in this is actually based on the shape model, but all the details here are purely artistic. We don't know what the surface looks like at this kind of detail yet. We'll know that when OSIRIS-REX gets there. Okay, so the rotation state is well constrained. As I mentioned before, we know the period quite well, and the small amplitude of the light curves are consistent with the radar model as being a fairly spherical body and it has a low albedo, as I mentioned. Okay, so one of the things that we're going to be able to do with Bennu, which is really exciting, is we're going to get to poke a stick at something called the Yarkovsky effect. The Yarkovsky effect, I've been fascinated with this since I was a graduate student, and I had to kind of puzzle out how it worked from the original Russian papers. I won't inflict those on you, but I think, at least give a very quick explanation of what's going on here. This is a non-gravitational effect. If you consider an object like this could be Bennu here with the pole sticking up perpendicular to the orbital plane, as it rotates, material comes into the sunlight and then goes back out of sunlight, and so it gets heated on this side and cooled on this side. And the hottest part of the surface is not right at noon, but in the afternoon where you've been heating the longest. And so the net result, and the coldest part's over here where you've been cooling the longest. So the net result is that the infrared radiation that's emitted by this body is not emitted isotropically, but you have a net emission that is towards the afternoon side. And this actually serves as a very weak thrust, basically, and it pushes the asteroid out. Now, if the asteroid's rotating in the other direction, then the afternoon side is over here, and the thrust is sort of in the leading direction, and so it actually slows the asteroid down and it comes in. So this causes objects to wander slightly off their gravitationally defined orbits. Now, if your object has got its pole tilted, then you get an additional effect, a seasonal effect. So here's one where we've laid the pole right down in the plane of the orbit, And here you get a net thrust when you have one of the poles left continuously in sunlight, and this also will shift you out of your orbit. So this effect can be rather complex because it can depend on the shape of the body, its albedo, its thermal inertia, exactly the orientation of the pole, and so on. So these are both sort of extreme versions of the simple case. These can have two profound implications. One is, of course, if you're worried about an object hitting the Earth, well, we already know in the case of Bennu, because of the radar data and other observations, we know that it's moved about this much a distance in this many years. So it's not a huge distance, but it's not trivial. And so there are two implications for this for asteroids. One, of course, is if you're worried about something hitting you, you better account for all the effects. So when Bennu makes a close pass, it may miss us at a position where it will miss it. We know it'll miss us on the next pass. But there are these little keyholes where if it passes through that little point in orbital phase space, our prediction is it'll come back and get us next time. Well, the Yarkovsky effect is big enough to help define whether you go through these keyholes or not. So that's one important consequence. The other is that it may be important for how asteroids actually get delivered into near-Earth space. When an asteroid is broken up into pieces and they're all spinning, you might imagine some will be in this state, some will be in this state. They'll start to wander in and out, back and forth, and that wandering might take them out of their original orbit into one where you're in a gravitational resonance with a large planet, and that'll start to pump it up and actually deliver it into a near-Earth space. And if you want to talk to someone about the details of that, and then talk to Bill Bakke, who's going to be talking this afternoon. He's been doing a bunch of really fascinating work on this and can even tell you probably for Bennu, which is a near-Earth space now, where it likely came from and what its parent body asteroid family might be. Okay, also having all this radar data and these other measurements gives us some huge advantages for the actual operations of the mission, because we need to know what orbits will be stable in, how the spacecraft will behave in the space. You know, operating near small objects like this is tough because there isn't a lot of gravity that you can count on to work with in an easy way, but you can't also ignore it, because if you do, you'll run into something. But it also, these shape models give us some hints of what the slopes are on the surface, because we can't just sample any place. We need to sample a place that's not only scientifically interesting, but also safe for the spacecraft. So just a few things about the timeline. Right now, we just passed CDR a little while ago, so we have permission to cut metal. We launch in September of 2016. We do an Earth gravity assist, and we arrive at the asteroid in August of 2018. We leave in March of 2021, so we're there quite a long time. I'll talk about this a bit more on the next slide. Sample gets back on the 24th of September 2023. I didn't look up the number, but I think I can tell you the nearest second when it'll be back, pretty much, because if it's not back that second, it's not going to land in the right place. Then the end of the mission is 2 years later, because we have 2 years to study the sample, at which time then the sample is, of course, turned over to the NASA Curatorial Office, and it's available for anybody on the planet to request samples or to do scientific analysis. So here's just a bit of a blow-up of the time we're at the asteroid. I won't go into the details, but basically we approach, and as we get closer and closer in, we learn more about the body. We feel like we can conduct operations in safer. We go in and we go to different stations so we can see the asteroid at different light illumination phase angles. We start to identify potential places where that might be good to sample. A lot of observations made here with instruments. I'll talk about it in a second. And then we slowly whittle down the sample sites to our favorite. And then hopefully we go down and we collect the samples successfully, and then we're done with that phase. If we have any problems with that, we're able to actually descend and try more than once. So it's not a one-shot deal. And then currently the way the plan works, we have a big operations margin. We're actually at the asteroid for much longer than we need to do all of this. But if we have any problems with any of these phases, any issues, we have more time to use, so we don't have to do anything in a panic. Okay, there's a number of instruments on board. I won't go into details, but there's 3 different camera systems that allow us to take images all the way from some distance away right up to SamCam, which actually will allow us to look at things really in close. So we'll actually get a good view of what happens when we sample the surface, see how the surface reacts. Be one of the ways we can verify whether we think we've gotten any sample when we go down. There's a laser ranger finder, which will help us generate a shape model of the asteroid and also be very useful for a lot of the operations in the near Bennu space. There's 2 spectrometers, OSIRIS and OTES, and they cover the visible out into the near far infrared. And these will be able to give us information about the thermal flux, thermal inertia of the surface. We'll get reflection albedo, and then if there are absorption bands in this object, we'll be able to see those. So we're very interested in things like if we can see carbon-hydrogen stretching bond absorptions in the surface. This would tell us an area where there's organics, for example. So these instruments will play some role in helping us pick out what might be good sampling sites. We'll do radio science while we're there, and then there's a REXIS instrument, which is a student instrument, which will look at, will give us elemental compositions of the surface. Okay, here's OSIRIS-REX with the sampling system deployed. Ross is not a part of the sampling system. He's just there for scale. Although I would point out, if you are on Bennu when we sample and it comes down on top of you, I'd suggest you duck, because there's not a lot of clearance there. So the sampling head is down here on a long arm. It senses when the spacecraft touches down and it bends. So this is not, we don't land, we sort of do a touch and go. Once it's down on the ground, it fires a bottle of nitrogen, pressurized nitrogen, high purity nitrogen, the same nitrogen that's used at the curatorial facility to store samples in here on the Earth at Houston. And this nitrogen comes out and fluidizes the material underneath and sweeps it up. I think the next slide shows a bit of a blow up. So that nitrogen comes down and it gets distributed to the edge of this sampler, where it's shot into the regolith, it fluidizes it, the regolith goes flying up and it gets caught by a screen right here, and then the spacecraft backs up and you hopefully have all the sample you want right in here. And this device has been tested in multiple ways, both on the ground and also on the low-G flights on aircraft, and it seems to work very well. Our goal, or our requirement, is to get 60 grams of material. We never get 60 grams of material. We always get way more than that. So that's encouraging. In addition, there are some contact pads on the bottom of this whose purpose is to just be pressed gently into the surface, hopefully, and pick up any dust that's just on that top couple microns of the surface. Because one of the things that's a real puzzle for telescopic data of asteroids is they often seem to be much redder than we see for the meteorite samples, we think, compared to them. And that may be due to space weathering, and that space weathering should probably be an effect which is just literally the very top surface of the asteroid. So we're hoping to bring back some dust which is just that top layer. We'll see how that works. Okay, and then I'll just end with this. These are other places you can go if you want to get more data on the mission. Everything seems to be going well, and we're really looking forward to a launch. And then I don't know if someone can wheel my wheelchair up here in the future, maybe I can talk about the samples that come back at some future meeting. So I'm happy at this point to entertain any questions you may have.
Great. Okay, we have some questions. Wait for the microphone. Wait.
But how do you know that you've got the right sample if you haven't done some kind of in situ analysis? I know you got remote sensing and all that.
Yeah, well, for in situ analysis, of course, is what we'll have is going to be any data from the instruments we have there. But largely, what those are going to do is give us some clues about what might be there, and also tell us something about whether the surface is homogeneous, or heterogeneous. I mean, one of the problems that's going to, I suspect this won't be the case at this asteroid, but one of the things that could plague us is suppose you get there and you find out the asteroid's a checkerboard. It's white here and black there. Well, you got one sample, or what do you do? Because then if you get white, then you're not sure exactly what the black is and how that, so you don't understand the whole object. Now, everything we have so far suggests this object's probably going to be more homogeneous than not, but anytime, this is one of the problems with sampling. I mean, I showed all the advantages of it, but one of the facts, it's not really so much a problem, but it's a fact you have to live with. When you get a sample, the sample has its own collection biases. Okay, your sample is only what your sample is. It doesn't tell you what your sample isn't. So, for example, if half of the asteroid is covered by gigantic blocks of concrete, we're not going to sample concrete. We're not going to bring back a concrete block, and so we would miss that unless chips of concrete have been blasted off by impacts, and some of those chips end up in our smaller samples. So you always have to be aware of the potential for bias. But the nice thing about having all these in situ measurements is that we'll know wherever we do land how that compares to the rest of the asteroid, and that'll at least give us a clue what our biases might be.
Okay, Tim?
Kind of following up on there, are there any scenarios in which you can do more than one touch and go?
Well, there's multiple scenarios for multiple touches and go. The main ones would be if you go down and you you don't get the sample you want. So there's two ways that could happen. One is maybe there's some system doesn't perform the way you want and you don't sample at all. The other possibility is that you sample and your best indications are you didn't get the 60 grams you want, that we require to get, in which case you could go down again and try to pile on to whatever you did get and put more in. If we have a successful sampling event, then we're probably done, because you don't want to go down and risk the sample you've already got to go again. I suppose if you had a black and white checkerboard, like I said, you could have a discussion about whether you wanted to go down, fire a bottle and get the white stuff, and then go down again on a black zone and do it. But I think there would be a huge uphill battle for that. But we are prepared to go more than once if it's necessary. The plan is not to go more than once.
Okay, great. Thank you very much, Scott. Let's thank our speakers for this morning, but before we leave,